they're going to split 50-50. Half of them will end up at the top, and half of them will end up at the bottom.
They're doing the same thing. They're always doing the same thing. So they're magnets. You said that everyone is emitting their magnets, electrons. What do you expect them to do, you moron, when you make the north and south go through and you put them exactly in between, 50-50?
Now this result, similar to in the light case, can only be explained by measurement collapse. To figure out what's going on in this experiment, we need to be able to talk about the quantum state of an...
So this is what quantum collapse is. Turning your magnet to another direction. That's a different quantum state, huh? Oh, this makes sense.
Can only be explained by measurement collapse. To figure out what's going on in this experiment, we need to be able to talk about the quantum state of an electron with spin. We have an electron that has already gone through a Stern-Gerlach machine just now and ended up.
Okay, so that means north is up and south is down.
So we want to represent this state as a quantum state. Remember, our first rule of quantum mechanics is that every quantum state is a vector. So we need a vector that represents this state. Well, this case is fairly straightforward. Let us draw this vector that represents the state of this electron as this arrow.
Keep in mind, this is a magnet with north and south. And she's going to plot it down like we can't figure out what north and south means.
And we're going to call it up.
Yeah, don't call it north.
Imagine that we put this electron through the Stern-Gerlach machine, and instead of getting the result up, the electron went downwards, and so this is in state down. How should we draw this state?
You moron! If I knew that electrons were little magnets, this is insane.
You might think that the best way to do it would be to draw it downwards, and that would make some sense.
Yeah, you want to do something that makes sense.
But actually what we're going to do is to draw it this way. Why would we do that? That's because, remember, this is a mathematical representation of the actual physical situation. And what we want to, encode in this representation is some relationships about these different states. So, for example, up and down are opposite states to each other. When you do a Stern-Gerlach experiment that's aligned in the up-down direction, each electron has to choose whether to go up or to go down. And it can't,
She's literally talking about a magnet. Okay, they all admit it. She admits it. They all admit it. They don't admit why, but they say it's intrinsic. I'm not debating whether the electron spins or not. If it has a magnetic field, you moron, that makes it a magnet. If that means it has a north and a south. That's what up and down is, you idiot. You said it. All the physicists are saying it. But somehow you don't understand how magnets work or something? I don't get it.
Both of those, because they're completely orthogonal to each other. And so, in that same way, we want them to be orthogonal in this representation. Things should be orthogonal in our mathematical representation, even though it doesn't line up super well with the physical representation. Now we have a basis for this measurement. Remember,
see how they have their up and their north and their south orthogonal? This is retarded, man.
A basis is a set of vectors like this that are orthogonal to each other, that represent all of the different possibilities of a particular measurement. So this particular measurement, this Stern-Gerlach experiment, has two options, up and down. And now we can use that measurement basis to figure out what happens to any electron in any state when it goes through this measurement. So suppose I have a state that is perfectly in between these two states. This state is a superposition of both of these two states. So as we learned last time,
so a superposition is when you have your magnet not up or down, but then you put it in this orientation. Really, that's a quantum state, huh? Putting your magnet in it. This is insane. If you have your magnet oriented this way, and this way, okay, on these, you got your X, Y, and Z axis, right, going in and out the dotted line. Okay, these are not quantum states of these magnets. They're just, you oriented them different. You oriented the north and south different, so that they're going on the X and Y, Z axis. They're not quantum states, okay?
The way to write this state that is at 45 degrees is, it is 1 on square root 2 up plus 1 on square root 2 down. What is this state, by the way, physically, with the electron?
Physically, you rotated it. You're just putting the north and south in a different direction. You're adding all this math for no reason, because you can't admit that the damn thing spins.
Way is its
and you can't admit that you can't see the electron. I can't see it. It's a blur. Oh, well then that must mean it's a big wave, and it's not really a particle. Do you know how small an electron is, dummy? You can't see it. It's a blur because your view is... Oh my God!
Waiting. Well, let's think about it. This state is like, it's completely unbiased between both up and down. And so we can't have, the magnetic moment pointing upwards or even a little bit upwards like this. That wouldn't make sense, right? Like this at 45 degrees, it's a little bit tempting to think it would be that, but actually this is very biased towards up. And so it should most of the time end up going upwards. But that's not what we find. We want something that's completely unbiased between these two. And so really, it should be like this. The magnetic moment just points off to the right. So this state is the right state. And how do we find the probability that this state will go upwards? Well, we look at up and we look at the coefficient and we take the absolute value squared of it. So
Really? You can't just say, if you put a magnet through here, right, and you have north on one side, south, and it's parallel, it's going through it, you can't just say, oh, 50% is going to go up and 50% is going to go down. You got to do all this math. I'm the idiot, huh? I'm the idiot. You people suck.
The probability of getting up is 1 on square root 2 squared, which is half, and the probability of getting down is 1 on square root 2 squared, which is also half. So this has a 50-50 chance of going upwards or downwards.
Yeah, it's a magnet, dumbass!
This is the other way of figuring out this probability. And it is going to seem a little bit needlessly complicated,
yeah.
But it is really nice to know. It helps you later on when you want to write things quickly and you don't want to be doing loads of calculations. Like, this way is probably the easiest way to be doing calculations.
I want everyone, if you got kids, I want you to go ask your 5-10-year-old, hey, if you throw a magnet through and you have it parallel, though, in two giant magnets, or you throw them all arbitrarily, they're all different directions. Do you think you're going to get 50-50, or do you think you're going to get, some of them just don't even get affected by the giant magnets? This is insane.
And figuring out the probability, but the other way is kind of nicer for sort of thinking more philosophically about quantum mechanics. Of course, I should point out, they're both exactly the same when it comes down to it. It's just a slightly different perspective. The dot product rule for figuring out probabilities in quantum mechanics goes like this. If you want to know the probability of measuring a particular vector, so this quantum state, the right state, as up, when you measure up down, what's the probability it will go up? The way to do it is to first calculate the dot product, or the inner...
I can't believe this is happening. She's talking about a tiny magnet going through two giant magnets. If they're all arbitrarily whatever, it's 50-50. If you put them in like this, where you're putting it through machines so you know they're exactly parallel, you're going to get a 50-50 thing, you idiot. This is retarded.
Product, as it's also called. Take the modulus of it and then square it. The modulus bit, by the way, doesn't really matter for us at the moment because we're only dealing with the case.
I'm curious if she gets the thing like that and she orientates the machine, because she's doing it orthogonal all the time. What if she rotated it just a little bit like that, right? We would all know that 100% of them would go towards the thing, right? I mean, if this is north and that thing is south, right? But I bet she'd be so confused, like, I wonder why.
Where these coefficients are real numbers if there were complex numbers, it would matter. But for now, we're not going to cover that complex case. I'll probably put that into an optional extra video, because I think the complex bit doesn't really add too much to the interpretation. As long as these numbers can be positive and negative, I think you get most of the interesting quantum effects. But anyway, just so you know.
Quantum effects from turning a magnet to a different orthogonal to where the north and south was. That's a quantum state.
So, okay, the modulus bit's not important, but how do you calculate this inner product? And what even is this inner product? What does it mean? Well, as I kind of alluded to before, it's a measure...
She's like so confused. She's so confused that magnets acted like magnets when she threw a bunch of magnets at another magnet. She's confused.
Of how lined up these two vectors are. So this vector and that vector, how close are they together? Are they overlapping each other? In which case this would be equal to 1. Or are they perpendicular to each other? In which case this would be 0. Or is it somewhere in between? In the previous video, I explained that the dot product of two vectors is cos of the angle between them. In this case, the angle is 45 degrees, and so the dot product is 1 on...
She's talking about throwing a little magnet through two big magnets. You don't need all this math, okay? This is ridiculous. I can't believe I can't get one person to admit this is crap. Now, I don't know if you noticed, she's just basically using statistics and probability math equations. You know, you get the... What's funny is you get this... If you pretend that the electrons that she's throwing through are magnets, and you don't even have to pretend because they are magnets, you get this, and you do the statistics and probabilities equations, you will get the same exact answers as her calculus there and her whatevers, you know. Why is that? Why is it that I get the same answers just using statistics and probability equations for regular magnets? I get the same exact probabilities as these quantum probabilities. So why is that? Can someone tell me that? So you can see the first video and a half was just them proving thing after thing. The balloon with the electrons on it make a magnetic field. The Earth is moving electrons, making a magnetic field. The test where they put the thing in and it toggled, proving it had and then they come to the conclusion, they're like, this proves it doesn't spin. No, that proves it does spin, you idiot. The only reason why they think that we can't spin is because they're saying the smaller, parts of a ball doesn't actually spin if this is spinning, the whole ball. Yeah, but so I could even say it would be logical if they said, well, so the smaller parts, if you took them out, they couldn't spin since they can't spin here. That would at least make sense. It would be stupid, but it still makes sense, okay? Just because the parts aren't spinning while the ball is spinning doesn't mean... The electron has no parts. You don't have to worry about that, whether the parts are spinning or not, okay? And when we say the ball is spinning, not one time have we ever said or thought that we were talking about the smaller parts. We are always talking about the whole part, the whole thing, okay? Whether we don't care if it has smaller parts or not, we never had. A basketball, if it was the smallest particles was basketballs, you could still spin a basketball, okay? But that isn't even the argument, okay? You do see how they're just taking the magnets and throwing them through here randomly and then lining them up so that they can put them through the next time, so the north and south are the same as this dotted line. You know what I mean? They're same path, we all know it's going to be 50-50, and then they switch it around, then they get that set that they just put into the same position that they put the last group into. They put it through, then they take these again, which are in the same position they threw them in, you know what I mean? And they get 50-50 every time. They're calling these things quantum states. They're saying if you rotate you have your magnet in the x axis, y-axis, z-axis, those are different quantum states. No, you just reoriented your freaking thing, man. And yeah, they changed this. Yeah, it's going to line up if they go by each other. Why am I the only one who sees how this is so insane?